Welcome everybody to the third PitchD of 2021. I'm Carmina Paolino and I'm presenting this event where our PhD students within Politecnico di Torino discuss their research with the IEEE members and our IEEE community. The speakers of today will be Mohammad Ghazi, Mohammad Amir, and Francesco. As usual, at the end of each talk, there will be a Q&A session, so please feel free to write your questions in the YouTube chat and we will provide it to the speakers. And to the students who can get some credits from joining in the event, just a quick reminder, we will post a form that you can fill. And yes, I guess we can start. The first speaker of today is Mohammad Ghazi Vakili from the Department of Control and Computer Engineering. He will give us a speech entitled the Industry 4.0, Industrial IoT Enhancement and WSN Performance Analysis. Mohammad received the Bachelor of Science in Telecommunication Engineering and his Master of Science in Mechatronic Engineering from Politecnico di Torino. He is currently a PhD student at the Department of Control and Computer Engineering in Politecnico under the supervision of Professor Claudio Giovanni De Martini. His research interests concern Industry 4.0, the future of factories, and focus on industrial wireless sensor network and IoT. Currently, he is working on the TSCH protocol on WSN, and he developed a simulator for the TSCH network for Industry 4.0 framework for small, medium enterprises. During his PhD, he developed many IoT projects, such as pollution monitoring station, the TSCH simulator at the IIG gateway, establishing an extended OPC IoT platform for Industry 4.0. Besides his main activity, he worked on quantum optimization for industrial sector to enhance industrial processes. Please, Mohammad.
Good afternoon. Actually, thank you so much for making this event happen for everyone, also for the IEEE members and also for the students. Today, I will talk about my research in the past 3 years, which I have done. Okay, 1 moment, please. I have done many activity, but what I have today actually we would like to share with you is about the wireless sensor network. My activity is Industry 4.0, so any work which I have done was around the domain of the industrial domain, like industrial wireless sensor network or industrial IoT. And I try to increase the reliability and latency in the industrial applications. But what is Industry 4.0? As you know, industrial revolution started many years ago, maybe two centuries ago. So in the 18th century. So when steam power came to the industry and start to change the industry. So the second industrial revolution was in the 19th century when mass production happened by using the electricity. And the third industrial revolution started in the 60s when engineer and scientists and researcher used the computing power and they used the programming language to program the machines and the robotics arms, and a lot of manufacturing, let's say, automation happened in the 60s. And the fourth generation, which we are living now in the fourth generation, is about connecting the physical world to the digital world. By connecting this, by creating this connection, we can use the power of the computing, power of the cloud computing, and we can create and we can optimize the production line, and we can create a new business model, such as customization of product and proposing the new product to the business owner to produce the new type of the product. But all this activity comes with the good communication and sustainable communication, which we will talk today. This talk will be around this communication, about the wireless sensor network and IoT, and how we could use these type of devices in the industrial domain. But next generation also, we should not forget for the next generation, which usually I mention it. And also during my past activity, I have done some small work around that. Will be using the power of the quantum computing to optimize our production line. Maybe in the future, we can call it Industry 5.0. Who knows? But this is something that we have to work on that as a researcher and as an engineer for the future of the factories. But I started to talk about the communication, but what does it mean communication, or what does it mean sustainable communication? Because as I said we need, Industry 4.0 talks about it connecting all the assets and devices in the shop floor to the top floor, which top floor, usually it means the clouds. Cloud computing and the servers, which is in the cloud, or fog, which is in the middle of the cloud and the shop floor. But the activity which has to be done is a communication. And usually IoT could help industrial application or industrial, let's say, or I can maybe simplify this, connecting the machines like CNCs, robots, and all this stuff to connect to the cloud. So IoT can help. But how we could use these devices and what condition they should have? Sustainable communication usually in the let's say industry categorized in 4 different categories as a performance analysis or performance indicator, they call it. They should have a high reliability, low latency, and low power consumption. Also, we could talk about the flexibility. Flexibility, it means possibility to connect to the different vendors. As you know, in the factories, when you go, when I'm talking about the factory and industrial communication, I'm talking about the shop floor. So in the real factory, which a lot of devices and from the different vendor installed, and they have a different communication protocol. So we are, as an engineer, we have to provide the secure channel and let's say, and communicate between devices in an optimized way. So this is very important. And using the wireless sensor network could help us to do this activity. And today we will see how we could, what is the problem actually, when I'm talking about the problem about the wireless sensor network, what is the problem? What is the challenges in the wireless sensor network when we come to the industry, or when we go to the factory, we see, okay, we have a lot of devices and we can install immediately, but what will happen after that? Also, I would like to mention one of the protocol which I work on that, and all today's talk will be around this protocol, which is a 6-ish protocol, which is a TSCH protocol, time scheduling channel hopping protocol via IP6. And I will show you what proposal we work and we propose to the 6-ish, let's say, community. We propose the mathematical model to estimate the performance indicators such as reliability, latency, and power consumption for the single and multi-hop networks. And at the end, I would like to share with you the latest, let's say, activity which we have done in our group about the TSCH simulator. TSCH simulator is a sort of predictor for the performance analysis, which it can predict the performance indicator of the network by configuring, TSCH matrix easily and giving very, it provides very user-friendly interface for the end user. So, but what is the problem? You know, when we start in the industrial IoT or wireless sensor network, usually we are working in the factory, and we try to segment, because we are working also in the Industry 4.0. Industry 4.0 has some requirement. So it starts by starting to work in the factory, we can see the factory plant. For example, we can segment in 4 parts, which one part will be stock management, which all your stuff will be stored there. We have also supply management. We have production line, which is responsible to produce the product, of course. And we have also the quality of the control, which at the end, after production line, we have to verify if this product is valid or not, or it fulfill the requirement that we have to fulfill or not. This is the concept. But we come to this type of factory and we try to apply the Industry 4.0. So Industry 4.0 says, okay, connect all the devices and all the places which the action happens, event happens, connect those data to the cloud. So you connect it with the IoT or wireless sensor network. And for example, wireless sensor network, they create a mesh network. So they connect it together. They are not using the Wi-Fi. They don't like Wi-Fi. They use the standard, which is the IEEE 802.15.4 is one of the standard, which is very useful and it's very common and frequent. I mean, common in the industrial application. It's very frequent to use. So then, of course, you will face with the Wi-Fi. Also, you will have Wi-Fi in these days. You will have Wi-Fi in everywhere. So, such as in home, in offices, and also in the factories, because everyone now has mobile phone, and this is something that is necessary to use. So, but the problem is when Wi-Fi comes to the factory, our wireless sensor network cannot work because they are working the same frequency spectrum, and they have they are sending data in a higher power, so more than the wireless sensor network, because wireless sensor network works with a lower energy, because they are working, they had to fulfill the low power requirements. So what you have to do, one of the activity which I have done last, let's say, 3 years was trying to propose the methods and the algorithms and also model to guarantee the industrial applications, let's say, or industrial domain to fulfill the requirement for the reliability and low latency. So just to remind you about the 2 things, because today I will talk about it. So single hop and multi-hop. Single hop, usually, just as a, let's say, reference, single hop, it means that all your leaf has one distance, just one distance between, there is one distance between the leaf and the root. But in the multi-hop, you have a more than one distance. So when we are talking multi-hop, it means you have a many layer until your packet travels between the leaf. But in the single hop, you have just one route. So you can send data with not a lot of latency. So it has some advantage and disadvantage, which is not concerned for this talk, but there are some advantage and disadvantage to use both of them. So it is not just one of them is better than the other one. And today also, I wanted to say all my, let's say, work was done with the OpenWSN operating system, and also by using the open mode devices, which is one of the latest WSN. I used because both of them are open source, and I was thinking to change something in the protocol. So I go with these 2 devices, not 2 devices, but 2 technologies. And they are supporting the 6-inch protocol. So easily we changed the protocols, and we did a lot of experiment, and we proposed a new algorithm to increase the reliability. And this is one of the actually activity which I have done. We proposed the model to the for the single and multi-hop network, we proposed a mathematical model. So it is not data-driven model. So we started from the Bernoulli trials, and we made all the model with the starting very simple assumption, and at the end we could data set. And with the data set which we had, we verified our model, and we saw our model could really with the 99% precision can follow our data set. And at the end we try so to avoid using the data set and define just the parameter and get the expected let's say performances, or try to estimate the performances. It is helpful because imagine when you want to install some devices in the factory and you want to do what you have to do. You have to simulate with the simulator, or you can try some very fast way. The model that we propose is a very fast, let's say, analysis to verify your performances and estimate the performances. Also, we published the model in the publication, actually, in the ad hoc network, Elsevier. And for the multi-hop, which because at the beginning we started with the single hop, then we moved to the multi-hop because multi-hop has a little bit difference between the with the single hop. We try to let's say extend our model to the multi-hop, and then we also include the power consumption. And after using the power consumption, we try to propose the optimizer. So now the model has optimizer also, so we could optimize the network automatically. So to give the proposed, let's say, a parameter for the 6-dish protocol, which also we try to test this actually protocol. As you could see here, we could also here in the power consumption, we could estimate the first one, the green one, is a real power consumption, and the blue one is a predicted, or not predicted, it's better to estimated power consumption, which we could estimate with our application. This is the first, power consumption also with a different, the different parameter in the network, which we have. I said we have different parameter in the 6-dish, and we try with the different also configuration, different parameter to see if we can reach to the expected, let's say, expected performances, and we could estimate the system or not. At the end, when we were working on the doing the experiment, we were trying to do the experiment by the real devices, and at the end it was very difficult because I forget to mention that we published also our data set, which we acquired and logged for this more than 6 months. So all the because there was not at that time there was no data set for the 6-dish protocol, and we published in the IEEE data port, which everyone which they are working in this area, they could use the data set to try to do some machine learning or anything that they want, or doing the data-driven model, or anything, or the work that they want to do something similar to our work, they can do, so they can continue the work. But during the activity, we faced with a lot of problem with the hardware, and we tried to do use the simulation, but or simulator, and we faced there is not good simulator for the 6-dish protocol, and they are trying just simulate the protocol, not simulate or estimate or predict the performances. So we try to propose very user-friendly and easy protocol, which cloned exactly from the real devices. And also it has a place, which we included the noise model inside. So we have a real, let's say, real environment, like a Wi-Fi environment. Imagine Wi-Fi environment and the electricity shock environment, which it is simulating also the whole network with this requirement. We try with the different, just to verify if our simulator or predictor works good or not. We try with different configuration, the latency, and we try to get the latency, reliability, and power consumption. And as you could see here, a standard deviation, which the top is for the real devices, and in the bottom is the simulated value. And also we can see also all more or less the system works more than 98% similarity they have, and also reliability and power consumption is the same, because if we have the same latency, we could reach to the same power consumption and reliability. It's in fact, this is one of our goals. And now I finished my talk. Actually, as I said to you, I work in the wireless sensor network, but mostly I work on the Industry 4.0. Just I wanted to show and share with you this picture from 1961, when third generation of the industry happened in the 60s. And in that time, it was one paper and journal, let's say, which they were trying to show the future of the factories. And in the picture was telling, okay, in the future, there is an agriculture plant which it can work automated, and there is no human actually action. There is no human action in the production line. But as you know, still we are far from this idea. Because of course the big enterprises they have, but what Industry 4.0 and why Industry 4.0 born was to push the small medium enterprises. And we are, as an engineer, we are responsible to make this happen. Today we will have also Francesco's talk, which will be around the Industry 4.0. I mean, we are working as a researcher to reach to that point, and we need, to push the industry to use our devices, or our technology. Thank you so much. And also I would like to mention thanks to the CNR of Torino, and also Politecnico di Torino, which make this research happen, and they support 3 years my PhD. Thank you so much. And if you have any question, I am here to answer.
Thank you, Mohammad. And thanks for the call to arms so that people can join in and lead to a faster development to Industry 5.0.
Yeah.
We have a couple of quick questions. So the first one is, is the factory environment becoming more electrically noisy as we go towards Industry 5.0? And how is the design phase of protocols or electronic systems affected by this?
Okay. Just at the beginning, I missed the voice.
Okay. The meaning is if we are getting a more noisy environment, when we go from 3.0 to 4 to 5, and if the design of electronic systems becomes more difficult.
Actually, yes, it is more difficult, because as you know, we are living in the higher frequency. So with the higher frequency, usually it's difficult to control the noise, and all the devices will be different. So exactly, it is very difficult at this moment also. A lot of people talking about the 5G, but I would like to mention this. 5G is not for IoT. It is for IoT, but not for the connecting devices to the higher level. 5G is for the connecting the backend. So it is for the let's say broadband network. So as we are working the, let's say, the frequency that is the Wi-Fi and wireless sensor network and other devices, they are very, very fragile. So we will miss a lot of data by just a small shock in the factory. So, and this is very important. Because of that reason, we try to use the TSCH network, or I mean TSCH network. It's very actually nice. If I can show you, just I don't know if we have time, just to show you. Because of that reason, okay, let me go exactly to the picture if it goes. Okay, as you can see here, the physical channel, which it is, you know, the physical channel which we are working in the reality with that, in each 20 millisecond, it's changing based on the random value in the communication protocol, in the 6-dish protocol. So it makes our work better, or let's say it increases the high reliability. This is very important. Also, it is important to make the physical channel, let's say blacklist and whitelist, which I work on that also too. So yeah, the question is right, but we are trying as a researcher to make the new protocol for the new environment, let's say, because as we are going through the new technology, we will face with the new type of problems. So this is the answer which I can tell.
Okay, so we need, I guess, a huge effort to move forward in this case. Okay.
Yes.
So thank you very much, Mohammad, for your presentation.
Sorry, it takes more than the expected time. So
yeah, I guess our viewers enjoyed your discussion.
Thank you. So I will stop the sharing.
Yeah, thank you.
Thank you so much.
The second speaker of today is Mohammad Amir Mansoori from the Department of Electronics and Telecommunications. He will give a speech entitled Hardware Acceleration for Microwave Imaging Algorithms. Mohammad received his bachelor and master degree in electronics engineering in 2013 and 16, respectively. He is currently pursuing his PhD in electronics and telecommunication engineering at Politecnico Torino. He is a Marie Curie Fellow as part of the Emerald project, funded by the European Union Horizon 2020 program. His main research interests include FPGA-based embedded system designs, hardware-software co-design using high-level synthesis, machine learning, and image processing. Thank you, Mohammad.
Thank you so much for the introduction. So let me share the screen. Okay. So before I start, I just want to grab your attention to this quote, that early diagnosis can save lives. So whether it is COVID-19 or it's cancer or brain stroke, the earlier that these diseases are diagnosed, the easier it will be for the doctors to treat the patients. And electronics engineering can help a lot for this purpose. My name is Amir, and in this presentation, I'm going to explain some of the electronics engineering techniques that can be used for speeding up the microwave imaging algorithms for medical applications. So at first, I'm going to explain what is microwave imaging and why do we need this type of imaging for medical applications. Then we will see some of the algorithms that are used in microwave imaging, and we will see which parts of these algorithms are computationally more complex. We call these complex algorithms kernels. And for these kernels, we can design specific hardware solutions to accelerate their execution and increase the speed of their execution. And finally, we will compare the final results with some reference designs. So microwave imaging is based on microwave radiations that are transmitted from a set of antennas through the body tissues. The reflection of these radiations are received by these microwave circuits and are converted into the image pixels by this processing block. But one problem that microwave radiations have is that they have lower frequency compared to X-rays or ultraviolet. And this results in a low resolution image. So the first question that arises is that why do we need a low resolution microwave imaging device? This is because other types of imaging devices like MRI or CT scan are very bulky and expensive, and they can be used only inside the hospital. So in the case of brain stroke, we have to wait until the patient is transferred to the hospital. And because of this, we will waste a lot of time. So instead, we want to use this microwave imaging device inside an ambulance so that we can quickly diagnose the brain stroke and determine which type of treatment we can select. So what are the algorithms that are used in microwave imaging? We start from the microwave measurements that can be interpreted as a scattering matrix. This matrix it shows the relative energy between each pair of antennas that are put around the body. From this scattering matrix, we can move towards two directions. The first is image reconstruction, and the second is anomaly detection. In the case of image reconstruction, the objective is to reconstruct the image pixels from the scattering matrix. In this direction, we have to solve an inverse scattering problem. And the solutions for this inverse scattering problem can be divided into linear and nonlinear algorithms. I don't want to explain the details of these algorithms. The important thing is that these algorithms contain computationally intensive parts that require a lot of time to be executed. For example, for the linear methods, we have eigenvalue decomposition, singular value decomposition, SVD, truncated SVD. And for the nonlinear methods, we have finite difference time domain that I will explain in more detail in next slides. Another direction is anomaly detection. In this approach, the objective is not to reconstruct the pixel values. Instead, in the case of brain stroke, the objective is just to determine whether or not we have the stroke. And if we have, what type of stroke do we have, ischemic or hemorrhagic, and what is the position of the stroke. In this direction, we can use machine learning techniques that contain feature extraction and classification methods. And again, we have some computational parts that needs to be executed, and they require a lot of time to be executed. So for the feature extraction, we have a principal component analysis, PCA. For the classification, we can use different classifiers like support vector machine, k-nearest neighbors, decision trees, and also multi-layer perceptron and even deep neural networks can be used in this framework. So the main objective of this research is at first to create a library of different microwave imaging kernels that we saw some of them in previous slide. And then for these kernels, we can design specific hardware solutions in order to increase the speed by using reconfigurable FPGA devices. And finally, we can optimize the performance in terms of processing time, power consumption, area, and so on. And for the design of the hardware in FPGA, we use a recent tool that is called high-level synthesis, that I will explain in the next slide. High-level synthesis, or HLS, is a tool that converts a software code written in C or C++ into its corresponding RTL implementation. For Xilinx devices, we can use Vivado HLS to generate the RTL IP. And in Vivado, we can do the placement and routing and implementation to generate the final bit stream. The main part of this flow in high-level synthesis is design optimization, for which we can use some kinds of HLS directives, and also we can do some changes and modifications to the C++ code. And this is the main part of the design, and we can design an efficient hardware in this part based on our application. For example, we can define proper hardware interfaces. We can use parallel processing in our code. We can use efficient data types and so many other optimizations that we can consider. So going back to our microwave imaging library, the first microwave imaging kernels, the first kernel that I am introducing you is finite difference time domain, or FDTD. It is based on Maxwell equations that imply any variations of the electric field will cause a magnetic field and vice versa. And in the left figure, we can see the flowchart of this algorithm. Given the dielectric profile of the simulation space, we can use finite difference approximations of the Maxwell equations in order to update the electric and magnetic fields in an iterative loop. We can see in the right figure that how FDTD can be used in a nonlinear image reconstruction algorithm in microwave imaging. Starting from an initial guess, the output of FDTD is compared with the actual microwave measurements, and based on the estimation error, we can use an inverse solution in order to update our initial guess. As we can see here, FDTD is the main and the critical part of the design, because it is an iterative algorithm both in time and in space. Because we have to compute these update equations for all of the cells in the simulation step space, and for all the iterations in the time step. So accelerating the execution of this FDTD in hardware can significantly reduce the total amount of time. To give you an insight of how much time we need to run this algorithm, we can look at this example. The original code for this algorithm was written in MATLAB, and the FDTD part was implemented in GPU by using a commercial software library called Axelware. So by using a GPU and with 1,000 time steps, and with this simulation space size, the time that is required for each iteration of this loop is 135 seconds. And if we have 30 iterations, the total amount of time will be about 1 hour. And obviously, this cannot be used in a real-time system. So in order to increase the speed, what we did was to develop our own C++ code for FDTD, because we didn't have access to the commercial software library Axelware. And after that, we checked the accuracy between our code and the commercial code. And then we used the high-level synthesis approach in order to optimize our code and improve the performance and convert it to the final RTL implementation in FPGA. So this was the first kernel in our microwave imaging algorithms. The other two kernels that can be used both in microwave imaging and in machine learning are principal component analysis and support vector machine. PCA, as I said, can be used for feature extraction and dimensionality reduction. It transforms the original data into its corresponding principal axis, and then by ignoring the least important principal component, we can reduce the dimensions of data without significant loss of information. For example, in here, the variations of data in the horizontal axis can be ignored, and then we can remove the horizontal axis, and we have only one dimension. For the support vector machine, it is a supervised classification technique that can detect a decision boundary between two classes based on maximizing the margin between these classes. So for these kernels, we can also design hardware accelerators in FPGA. And this is our FPGA accelerator of PCA. Again, I don't explain the details, but this design contains of two functions, dispatcher and a PCA core. And the first one reads the input data from the external memory and transfers them through this set of FIFOs into the next function. And then in here, there are several compute units that can compute the output and write it to the external memory. What is important in here is that, as we can see, there are several compute units in this function, and each of them can be used for different algorithms. We have, for example, here we have a singular value decomposition, SVD, that is another kernel in microimaging algorithms. So we can use individual blocks from this PCA algorithm, and we can use them for other types of algorithms in microimaging. In the case of machine learning classifiers, including SVM, we have to consider two phases, training and inference. The training is usually executed offline in software because it's only done one time. It receives the training data set that contains different positions of a stroke and different types of a stroke, and it can learn how to predict a new input data. So the inference part receives the training parameters that are obtained from the training phase, and it can predict the new input data, that is the scattering matrix, and obtain the type of a stroke and the position of a stroke. And the inference part usually is implemented on hardware and in FPGA, and this is what we considered in this research. For the evaluation of the results, we compared the performance of PCA for our HLS implementation and compared it with a manual RTL design. And we used the same data sets that are used in the reference. And as we can see in our HLS design, we could consume significantly lower resource usage, especially for the DSP48. And also we could achieve a lower execution time compared to the RTL design. We also considered both the floating point and fixed point designs. And we can see that for the fixed point design, the execution time or the latency is lower, and also we can support larger input dimensions. And for the FDTD performance, we measured the processing time for the FPGA design, and we compared it with the CPU and GPU implementation. We also considered both the single and multi-FPGA platforms. The advantage of the FPGA is that it can support more number of antennas to be executed in parallel. In the case of CPU and GPU, the maximum number of antennas that can be executed in parallel is only one antenna. But for FPGA, it can increase to 3. And for the multi-FPGA case, with 8 FPGAs, we can process 24 antennas in parallel inside the multi-FPGA platform. And by comparing it to the previous example that used the GPU for the implementation, it took about 1 hour to obtain the final image. And by using the multi-FPGA platform, it can be reduced to just 5 minutes. In conclusions, I explained some of the algorithms in microwave imaging. They can be divided into 2 parts, image reconstruction and anomaly detection. For the first category, I explained the FDTD algorithm. And for the second category, we saw how we can use PCA and SVM in microwave imaging. We can we can optimize our hardware in FPGA by using high-level synthesis. And we saw in the results that FPGAs can also achieve comparable performance compared to GPU designs. And in the future, we want to update the microwave imaging kernels, and we can evaluate the final performance in FPGA. And again, we can make a comparison between different platforms. So thank you so much. I couldn't explain all the details of the design and all the results because some parts of the results are still under review for the publication. But I just wanted to give you an insight about my research and what is my research topic about. So thank you so much. And if you have any questions, I'm ready to answer.
Thank you, Amir, for your talk and also for pointing out that the key to a better future is early diagnosis and prevention, which is a very important message.
Yes.
We have a few questions. Okay, the first one is, how do health professionals react to the imaging solutions and analysis you are proposing?
Well, as I said, our objective is just the diagnosis of the diseases. So what we do is just to either reconstruct the image, so the doctors, the health professionals can look at the image and detect themselves that whether or not we have the stroke, or we have the other type. So the output will be just the detection, and the doctors can see which type of a stroke we have, which is the position, and this is how health professionals can use these outputs.
Okay, so you are providing both a way of getting a faster imaging and some suggestion on the analysis of the imaging, right?
Yes. Actually, our objective is just to evaluate the performance of different kernels that can be used in different applications. So
okay.
Yes, the final output depends on our application, which one can be used. It's actually, I mean, because for example, if we have a very small problem, like if we have if the stroke is if the target object is very small, we can use linear methods, and for this we can use different kernels. For the nonlinear approaches, we need more accuracy, so we have to use different and more complicated methods. So it depends on what we need, actually, what the doctors need.
Okay, thank you. We have another question that says, I understand that the PCA is used to reduce the dimensionality of the features.
Mm-hmm.
Are
Yes.
the variables collected directly from the sensors? And if so, how many of the sensors are used?
Okay, the input to the PCA algorithm, basically the input is this scattering matrix. So this is, and it depends on the number of antennas that we have. For example, if we have 24 antennas, we will have a 24 by 24 matrix. And this will be the input to the PCA algorithm. And also, if we have different frequencies, for each frequency, we have a separate scattering matrix. And then if we have redundant information in this matrix, for example, if some pair of antennas have similar information or they have redundant information, we can use PCA in order to remove those information. I don't know if I could answer the question.
Yeah, I think you answered it. I mean, do you have some information on the number of antennas that you can manage?
As I said, the typical number that is used in a prototype in Polito is 24 antennas. So
okay,
the dimension will be a 24 by 24 matrix.
Okay, we are done with the questions. Thank you, Mohammad, for your presentation again.
Thank you. Okay, so I will stop sharing.
Yes, thanks.
Okay.
The third speaker of today is Francesco De Pace from the Department of Control and Computer Engineering. He will give a speech entitled Assessing the Effectiveness of Enhanced Virtual Reality Systems for Accurate Robot Teleoperation Tasks. Francesco received the Master of Science degree in Cinema and Media Engineering from Politecnico di Torino in 2016. He is a PhD student at the Department of Automatica and Informatica of Politecnico di Torino under the supervision of Professor Andrea Sanna. His research interests include the human-computer and human-robot interaction, augmented reality, and virtual reality. He is particularly interested in applying virtual and augmented technologies with industrial robots to improve the human-robot collaboration area. Please, Francesco.
Okay, thank you for the introduction. I'm just going to share my screen. Okay. Okay. Hello, everyone. I'm Francesco De Pace, and today I'm going to talk about one of our last research projects called Assessing the Effectiveness of Enhanced Virtuality Systems for Accurate Robot Teleoperation Tasks. This project has been done in collaboration with two other departments from New Zealand, the Emphatic Computing Lab from the Bioengineering Institute, and the Department of Mechanical Engineering. This year, I spent 6 months in New Zealand, and I had the opportunity to collaborate with them. Specifically, the Emphatic Computing Lab is specialized in the development of mixed and virtual reality interfaces, whereas the Department of Mechanical Engineering is specialized in the robotics and automation areas. Let's say I worked as a sort of bridge between these two departments, trying to develop virtual reality interfaces to control robotic arms, such as the one displayed here. So let's start from defining what is an immersive virtual reality interface, and then we'll move towards the so-called enhanced virtual reality ones. So virtual reality interfaces, VR, is an interface that allows users being physically present in a non-physical world. Normally, one of the most common devices employed to experience immersive interfaces are the head-mounted displays, as shown in this picture here. These devices are equipped with motion sensors that allows to compute the head rotations in terms of yaw, pitch, and roll, whereas the position of the head is normally tracked using external tracking sensors. In addition, in order to interact with the virtual environment, normally the manufacturers provide controllers, 6 degrees of freedom controllers that basically allows to compute the position and the orientation of the end in the 3D space. There are several types of controllers from different manufacturers, and also special gloves that allows to basically compute the position and orientation of each fingers. Let's say that this kind of interfaces has been quite researched in the telerobotic field. Basically, there is a sort of shift from the so-called pre-modeled environment towards the real-time scanned environment. With pre-modeled environment, I mean that the robotic cell and the factory are have been pre-modeled using CAD software such as Blender, Maya. I don't know if you're familiar with. So basically, there is no real reconstruction of the real space. Whereas then after that, there's been a shift toward the pre-scanned environment, as shown in this video here. Basically, the factory or the robotic cell is scanned using dedicated sensors such as RGB depth cameras. And basically, there is a sort of one-to-one match between the reconstructed environment and the real one. But again, it's done offline. Everything is done before interacting with the environment. Let's say nowadays we are instead moving towards real-time scanning environment, and we'll see them later more in depth. But basically, they exploit the same technologies of the pre-scanning environment, so these RGB depth cameras. But they, this environment use these cameras to capture in real time the real environment that is streamed over the network and reconstructed in real time at the user site. But what is important to stress is that independently of the environment, the operator can control the robot using the immersive VR device, as shown in this picture here. Basically, you are immersed in the virtual environment. You can, for example, virtually grab the end effector of the robot, and you can move it around. The other concept is that the virtual and the real robots are coupled through a digital twin. A digital twin is basically a strong link between the real and the virtual robot. Basically, for example, when the robot moves towards a specific direction, the virtual one moves accordingly, and vice versa. So regarding the last, the real-time scanning environment, basically, as I said, this environment are characterized by the acquisition of the real environment in real time using sensors. The data is transmitted over the network and reconstructed in real time, and the operator can control the robot using an immersive VR device. As shown here, this is a research paper done by MIT. Basically, to give you an idea, the user is immersed in the virtual environment. Everything you are seeing here is captured in real time using RGB depth cameras. That could be, for example, the Kinect sensor. And then you see that the user is virtually grabbing the end effector of the robot, and the real one is moving in real time. And this is the camera that is positioned in front of the robot in order to capture the environment. And I will refer to this kind of system with the term enhanced virtual reality system, EVR. Usually, these teleoperation systems are employed for pick and place scenario, as shown here. Basically, pick and place means picking an object and moving toward a desired goal, but the trajectory between the two poses is not important. Instead, there is a lack of studies that analyzes the effectiveness of the VR interfaces for robotic tasks that require high accuracy, such as surgery, welding, and painting. These kind of tasks are characterized by, the trajectory between points is really important. So we try to evaluate this kind of interfaces in such tasks. In order to do so, we develop our custom solution of EVR framework. This is just a high view of the framework. Basically, it's characterized by two different environments, the local environment and the remote one. The local environment is composed by a real universal robot UR5 and two IntelliSense D415 cameras. These cameras basically can capture both RGB information, color information, and depth values. And they basically reconstruct a 3D representation of the real environment. We develop a custom solution to stream the camera frames over the network towards the remote environment. In addition to the camera frames, also the joint configurations of the robot are streamed in order to establish a communication between the real and virtual robot, the so-called digital twin. So all these data are streamed all over the network and basically used in the remote environment. By using an immersive virtual reality device, the user can see the reconstructed environment and the virtual robot that moves in the same manner of the real one. And on the contrary, on the other direction, we sent the pose of the pose, I mean, in terms of the position orientation of the joystick on the network in order to control the end effector of the robot. In order to analyze the effectiveness of such interfaces for accurate robot tasks, we compared 3 different kinds of interfaces. The EVR, another one is called EVRR, that is basically an EVR version with a CAD model of the robot superimposed on the real one. With this, I mean, if you see here, this is the EVR, so everything is captured with the cameras. The EVRR is this one, where you see everything is still captured with the cameras, but you see that there is a virtual representation of the robot superimposed on the reconstructed one. This is the reconstructed, it is hidden behind. We did this in order to understand whether the visualization of the robot could improve the control of the robot itself. And the other one was a pure classical immersive VR interface, pure VR, where you have a nice representation of the robot, but basically you lack all the information regarding of the surrounding of the robotic cell. And this is the real robotic cell. So you have to imagine that we place the real sense camera in front of the robot, and they are capturing the environment. And this is streamed over the network towards the remote environment when the user can interact with the immersive VR device. This is a small video showing the EVRR interface. So, so basically, just to explain to you, this is me. The central video is showing what I'm seeing. This is me, and this is the real robot. Basically, as you can see, you can freely walk inside the virtual environment. You can also teleport. Basically, you can teleport whenever you want because it is virtual. And then by using the joystick, you can control the movement of the robot. As if you notice, when the virtual robot moves, the real one moves accordingly. And basically, we try to understand whether this kind of operation is suitable for accurate robot tasks. Yes, so in order to do so, we involved 18 users, and we asked them to perform 2 different kinds of tasks, pose task and speed task. Pose tasks are characterized by, basically the users had to position the real and the virtual, of course, a robot end effector. With end effector, I mean the last part of the robot arm. They had to position the end effector in a very specific position of the 3D space, and this position is highlighted using this virtual asset here. So basically, they have to move it in this position. And this is for the pose task, whether the speed task, during the speed task, the users, it's this one, the users have to move the robot end effector along a very specific trajectory highlighted in purple with a very specific velocity. To do so, basically they had to match the position and velocity of this green asset here that is moving along the trajectory. This is what's one of the tasks they had to carry out. And basically we collected 2 different kinds of data, objective data and subjective data. Objective are the end effector pose for the PT task and the end effector trajectory of the ST task. I forgot to mention that for both pose and speed task, both the goal poses and the trajectory have been pre-recorded with the real robot to ensure a common baseline. And we also analyze the subjective data. During my research, I'm mainly interested in the human-computer interaction. So we stress to analyze also the user performance, not only the objective data, but also the subjective one. Oh, sorry. To do so, we analyze the usability and the workload of the interface by using two well-known questionnaires, the System Usability Scale Questionnaire and the NASA Questionnaire. In addition, we try to evaluate the attention, spatial situation, and presence of the interface. That means whether the visualization of the interface, the robot and the surrounding could affect the effectiveness of the interface. These are the main results. I try my best to explain. Basically, they are divided in pose, speed, and questionnaire results. The pose, basically, the green are the best results, yellow the average, and the red the worst one for all the tables. Basically, when you see something like VR, EVR, and there is a sort of value equal or different to 0, there should be something. It means that there is a statistical significant difference between these two kinds of interfaces. So to give you an example, for the first task, VR, these numbers are the sort of errors. Lower is the result, better is the interface. So the VR perform better, followed by EVRR and EVR. But what is important is that we could only detect statistical differences between VR and EVR and EVRR and EVR. And this, let's say, apply for basically all the results. This means that we can be really sure saying that the EVR interface is not the best one, actually it's the worst one. But because both VR and EVR are better than this, but we cannot say nothing about the differences between VR and EVRR because there were no statistical significant differences. So it means that they can be the same. Generally, VR performed better for mostly all the tasks, but for, of course, the spatial situation presence section of the questionnaire, because since the users could not perceive the surrounding of the environment, they could only see the robot. Basically, they couldn't understand where was the location, where the operative area, and so on. These are just some considerations. So generally, VR is the best one, but unfortunately for both VR and EVRR, which were the best, the errors were still in range of 1 centimeter, which is still insufficient for a high precision task like welding. We need to improve the control algorithm. What is clear, I think, is that EVR is not adequate to control robotic arms. And this is quite contrary to the common state of the art, because for pick and place scenario, no one detected any anomalies, but for high accuracy tasks, there are. Because the EVR interface, the pure one, carries artifacts. With point cloud, I mean the visual in point cloud are the data carried by the EVR interface. And if you see, there are artifacts because close to the edge of the objects, basically the resolution of the camera is not enough to clearly basically the background and the foreground are rendered the same level. So there were some sort of artifacts that really negatively affect the visualization of the robot. And moreover, the point cloud by nature is not stable. It changes every frame, generating unstable virtual meshes. So our future work had to improve the point cloud visualization and the related streaming by applying machine learning techniques to recognize the real objects. Imagine being able to recognize the table, the objects. Once recognized, you can replace them with their CAD models, stabilize the visualization, and reduce the data transmitted of their network. And of course, we'll try to improve the control algorithm, try to tune the mapping between the movement of the user's arm and the displacement of the robot and the fetter. Yes, these are some pictures from New Zealand experience where I spent there 6 months this year, and this is me in the lab with one of my friends where we were developing the system. Yes, this is it. Thank you for the attention.
Thank you, Francesco. We have a few questions for you. The first one is, you have shown that you can drag the robot at the end effector, and the robot reacts with its own kinematics. Could you use several sensors along the arm of the user to capture more data, and do you think this will improve performance?
Well, okay, let's say, I'm just looking for the slide.
Yeah.
Okay, maybe, okay, to improve the control, you can, of course, add sensors to improve the control of the end effector. But what we would like to try is not adding more sensors to capture data related to the position of the user's hand, but to the robot itself. Basically, if you can add, for example, proximity sensor to the end effector, trying to understand the distance between the end effector and, I don't know, an obstacle. So basically, it could reduce the speed when the robot is approaching towards the surface. So try to develop an interface that is not completely controlled by the human, but I would call it such as a percentage control. Basically, the user can say, okay, robot, you can do whatever you want, you have total control. Or I can say, maybe I have 40% of the control, it's up to me, and the 60% it's up to you. Try to collaborate with the robot to improve the control itself.
Okay, so this would mean that the user has more feedback from the robot.
Yes,
this is
exactly.
The increase in data is one directional.
Exactly.
Okay. The next question is this kind of interface already more precise than using only a joystick and a non-immersive screen?
Okay. Yes, I mean, there's been quite a lot of research in this area. Basically, what appears is that in this work we didn't compare to a common video interface, because we already know that with just a video interface you lose the perception of depth. It's really difficult moving the robot not in the horizontal plane, but I mean not in the vertical plane, but in the horizontal one. Whereas using immersive interface, since you are there in a 3D world, you can freely move around and see the task from all perspective you want. And this is far more better than controlling from a common video one. For this reason, we didn't compare it with a video interface, because we already knew that is some way superior than the other.
Okay, thank you. And the last question is asking for some applications for this VR technology.
Okay. Yes. Okay. Application could be, if we improve the control algorithm, I mean, it could be, for example, this freak here, surgery, welding, and painting. For example, painting is for cars. Imagine it's shown here in the picture. Basically, you have to be enough precise to paint the car parts, but not so precise at 1/10 of millimeter, because these robots are really precise. But for several type of applications, it's not necessary to be so precise. And so painting is one of that. For welding, basically you can also teach the robot the movement, because another kind of task that is normally done to teach the robot sort of movement. Normally the approach is the so-called kinesthetic approach. With the kinesthetic means you physically grab the robot and move it around, and the robot memorizes all the poses and trajectories. This is good, but it's not so, it's really slow. And it has been demonstrated that using virtual and augmented reality interfaces, you can achieve better performance in with lower time. So yes, I mean, I think you can teach the robot. The objective is teaching the robot a sort of new movement for this kind of task here: surgery, welding, and painting.
Okay, thank you very much.
Okay, thank you. I stop sharing.
Yes, thanks. And now, before we go, we want to give a virtual reward to our speakers. If you want, you can turn on your camera. It's just virtual certificates you will receive in your email, in the hope that when we will live in better times, we can gather together and have the true certificate, and maybe also our t-shirts, which are highly desired by our guests. Thank you a lot for your interesting presentations. We run a little longer than usual, but I hope our viewers enjoyed the content. And thanks again also to the people that are working behind the scenes and organized everything. I guess this concludes the event. Thank to the speakers again, and thank to the viewers. See you soon for the next event.
Thank you. Thank you.
Thank you.
Thanks.
Bye.